Hello everyone. In the previous video, we talked about Taylor series, which were a way to write the power series representation of a given function. However, we did not address which values this representation actually agrees with the function. In this video, we will answer this question using Taylor's theorem. The idea is going to be to approximate the function by partial sums of the series, and then show that this error goes to 0. So first, we define the nth Taylor polynomial of f to be the partial sum of the Taylor series given by the 0 through nth terms. Now, we define Rn of x to be the difference between f and its nth Taylor polynomial. In other words, this is the error in approximating the function by its nth Taylor polynomial. We can now state the main idea of this video, which is Taylor's theorem. Taylor's theorem says that if the limit of Rn goes to 0 as n goes to infinity on some interval, then f of x is actually equal to its Taylor series on this interval. The underlying idea here is not too complicated. If the error in approximating the function by its nth Taylor polynomial goes to 0 as we take bigger and bigger n, then the limit of the Taylor polynomials, which is the entire Taylor series, approximates the function perfectly. However, it's not as straightforward to implement the theorem in practice because it can be hard to get a handle on this error. Luckily for us, there is an inequality that makes this a little bit easier. It's called Taylor's inequality, and it says that if the absolute value of the n plus first derivative of f is bounded above by a number m on some interval, then the error is bounded above by m over n plus 1 factorial times the absolute value of x minus a to the n plus 1 on this interval. If you think back, this should remind you of the error bounds we talked about when we discussed the midpoint, trapezoid, and Simpson's rule. It can be applied in exactly the same way to approximate the value of a function by using its Taylor polynomials. However, we're going to use it to show that the error goes to 0 in some particular examples. First, let's try to apply it to the example f of x equals sine of x centered at a equals 0. The goal is to find the values for which sine of x is equal to its Taylor series, which we computed in the last video. To do this, we need to find for which values the error goes to 0. We'll do this using Taylor's inequality. First, notice that all derivatives of sine of x are either plus or minus sine of x or plus or minus cosine of x. In particular, the absolute value of all of the derivatives are bounded above by 1 for all x. So we use Taylor's inequality with m equals 1 to find that the error is bounded above by 1 over n plus 1 factorial times the absolute value of x to the n plus 1 for all x. Now, we notice that the right-hand side of this inequality goes to 0 as n goes to infinity. Here, we're using the idea that factorials grow faster than exponentials. So, since the upper bound goes to 0, the error must go to 0 as well. Thus, by Taylor's theorem, sine of x is actually equal to its Taylor series, which we found in the last video, for all x. Now let's do the same thing for e to the x. We know that all derivatives of e to the x are e to the x. And so, to apply Taylor's inequality, we need to find an upper bound for e to the x on an interval. If we take the interval from minus d to d, then since e to the x is increasing, the biggest e to the x gets on this interval is e to the d. Therefore, by Taylor's inequality, the error is bounded above by e to the d over n plus 1 factorial times x to the n plus 1 on this interval. And now, just like we saw before, the right-hand side of this inequality goes to 0, and so the error also goes to 0 for all x in this interval. However, this was true for any d. Therefore, we can apply this argument to bigger and bigger intervals to show that e to the x actually agrees with its power series for all x. Now that we know for which values these functions agree with their power series, we can apply these to some examples. First, this allows us to actually compute the sum of certain series. For example, let's compute the sum from n equals 0 to infinity of 2 to the n over n factorial. Notice that this looks very similar to the Taylor series for e to the x, with a 2 plugged in for x. Therefore, the series evaluates to e squared. We can also use these Taylor series to find power series representations of other functions. For example, let's find the power series representation of cosine. We could go through and apply the methods from the previous video to find the Maclaurin series just like we did for sine of x. However, now that we know a power series representation for sine of x, we can use that to find a power series representation for cosine. In particular, cosine is the derivative of sine of x. And so, if we differentiate the Taylor series for sine of x, we get the sum from n equals 0 to infinity of minus 1 to the n times 2n plus 1 times x to the 2n over 2n plus 1 factorial. Here, we have to be careful since the series we are differentiating does not have a constant term, and so we don't raise the starting index. Then, we can cancel the 2n plus 1 on top with the 2n plus 1 included in the factorial on the bottom, and we get the sum from n equals 0 to infinity of minus 1 to the n times x to the 2n over 2n factorial. And this is the Maclaurin series for cosine. Finally, we can use power series representations to evaluate certain limits. Let's look at the limit as x goes to 0 of cosine of x to the 5th minus 1 over x to the 10th. You may notice straight away that this is an indeterminate form. Therefore, we could evaluate this limit by using L'Hopital's rule. However, since the powers on x are so large, this would take forever. It turns out there's an easier way using power series. Let's substitute in the power series for cosine of x to the 5th, which looks just like the power series for cosine of x that we just found, just with an x to the 5th plugged in for x. And now, to see what happens more clearly, let's write out the first few terms of this series. We see that the first term of the series can cancel with the minus 1 from the limit. And next, we can divide all of the terms in the series by the x to the 10th. And now we want to take the limit as x goes to 0. The key here is that all of the terms, except for the first term, have x's in them. Therefore, when we take the limit as x goes to 0, all of these terms go away, and we'll be left with just the first term, which is minus a half. All right, everyone, that's all I have for you today. I'll see you next time when we talk about more applications of Taylor series.